So as I mentioned before, we do a lot of processing in progressive mode, and I'll just show a few slides about the general principle behind this, but then we'll go to a couple of practical applications.
Valerio, sorry, there is a bit of echo. I don't know if you have...
Still the echo?
Yes.
Okay. What about now?
Same.
Any echo? Okay.
Yeah.
Yeah, so I was trying to listen, but okay, so this is kind of the general layout of how we design applications in VISUS. There is a data storage component, and actually that's all you need where you're doing the simulation of what we did at the first step. But then when you build a data processing or a visualization environment, there is a set of progressive algorithm. Then there's the whole architecture, the data movements, and that comes together in the tools that you have seen so far. There are different algorithms that can work better or worse in a streaming environment. So we don't promise that everything works super fast, but we have done a number of tests to demonstrate that this type of technology works in a very general setting. The idea is that we store data in a resolution fashion, but without need to follow traditional approaches that take all the data set and coarsen it. We actually go from the top down, build an approximation, so we don't have to move all the data when we do our trade-offs of quality versus speed. And the challenge was to show that the gap between the two is small enough, and we actually demonstrated this in practice. And the advantage is that you can do very deep pipelines of computing things in streaming mode without loading the data altogether.
Valerio,
so those are a few examples. In this case, for example, there is a pipeline for taking two high-resolution images, do the difference, segment some region, and I'll show something similar to this within our viewer. And as you can see, the time is much faster than loading any of the images, again, because we apply this principle of progressive streaming computation.
Valerio,
this is a different example where we're doing content-based image processing. We're looking for roofs in a city that are similar to the one that we're selecting now. It's kind of reddish roof. Now the image that we're dealing with is 300 gigabytes. So you're finding a feature that has some parameter, and instead of having to load and go through the whole thing, we can in real time explore it, and we're still able, as you can see in a second, that we actually can even change the similarity parameter without running the whole thing.
Valerio, can you hear me? There is still echo. Try now.
Maybe here.
Okay, now it was good. Try to speak, Valerio.
But I can take it all together. I said that I use the phone or something. Yeah. Is it better now?
There is still some. There is still.
By the way, Steve, I cannot hear you at all, so if you had anything, send me a text.
Yeah.
And so we try this in other applications as well. Again, the principle is really just to show that things can work in a very general setting. In this case, we're stitching together a large number of images. This is over a few hundred. Now we're more in the thousands or tens of thousands. And to do something like this requires to solve a global Poisson system. So this is one of the cases that was not supposed to work, and in fact we can do it and also do it in real time. And so this is an application where we take that technique, we take this whole 300 gigabytes. Looks like they still have echo, and so Steve,
it's okay.
Is that okay now? Is that because I was away from the laptop? is still okay, or?
Oh, okay.
Yeah.
He's saying this is no echo now.
No echo now.
Okay.
And so you see that we can take this massive image, solve for 300 billion nodes, this Poisson system, and then in real time flip from the original to the blended color and embedded in many different irrigation in real time. This is something that previous technology would take days, with higher computing, maybe hours, and certainly not something that you could do in real time. And just a point in the scaling of the technology. So we tried a number of different hardware platforms, especially on DOE machine, but also in other locations like Chaos, where they have the Shine computer. And PIX library that Georgie was demonstrating at the beginning actually scaled much better than other technology that are the equivalent of like standard library like HDF5 and so on. In particular, we don't have the problem of being stuck at 32,000 core. Because of the way we structure the data, we can basically pick the sweet spot and scale. In this case, was in the Mira supercomputer at Argonne National Lab, and we scale about over 80% of the nominal IO speed, all the way up to 750,000 cores. So, and recently we got involved in some of the exascale computing projects, so we will keep having access to those machines and pushing the parallel computation. I don't remember how much this was tested on the K computer, but it's going to go away soon. So as soon as maybe the next machine is going to be available, we'll try again and see that we push the hardware. And what influence this is going to be the Tower network and the file system. So we try that on Factory, on Dragonfly networks, on and various Lustre and other file systems. So this is the server that you just saw, and this is the case where we have been connected to a acquisition from a microscope. So it's kind of the equivalent of what Georgie was showing before with a running simulation. In this case, this is a collaboration with the team on neuroscience. They have this two-photo microscope. They generate these really large volumes, and they run this for weeks. And with our technology, they can monitor even from home what's going on, and then if something needs fixing, they can just go and do it instead of running the risk of wasting a lot of resources. So this is a test that a couple of months ago Steve has run from Argonne National Lab. It's a nice example of doing things geographically. They were acquiring data from a synchrotron light source APS near Argonne, so it's near Chicago. And the senior members of the team were actually here at the University of Utah, where we are located. And so with the streaming capability that you saw before, equivalent, but this is for imaging data, very high resolution. They could monitor how things were executed and being able to give guidance to the people on site. And I don't remember who was interested in climate data. This is a case where we work with NASA for one of their larger data sets. It's about 3 petabytes of data, and we created a mirror at Lawrence Livermore National Lab. And then in streaming mode, we allow to do ensemble computation, put things together, stream the results. Before, they were only able to publish a bunch of still pictures pre-computed, and in this way, actually, one can start doing some still experimental, but they were able to do some real-time computation, take away from an ensemble outliers, things like that normally would take a massive computing infrastructure. And here is just the actual numbers of the scaling, especially I/O computing, kind of all the way to iPhones and iPads, smaller data sets, laptops, powerful displays, larger servers, and all the way to the larger machines. So this is kind of the largest run we've done so far. Hopefully with the new machines available, we'll push it even further. What makes us very optimistic is that in the library, we are very flexible, saying how many files we create, how big they are. So normally other libraries get stuck because, for example, either they ask to create a single unified file or just one file per core. We actually can tune it. You can do one file per 10 core, per a quarter of the machine. You can hit the right ratio. So it has all the flexibility to tune it for different architecture.